So we'll talk through the question sheets. Photons. So as you saw in the clip, light, for example, travels as a wave, but when it arrives and is being measured or received by something, it actually arrives in lumps of energy or a packet of energy. So we have this whole wave-particle duality thing where light is a wave in terms of how it travels somewhere, but a particle in terms of how it delivers energy in lumps or amounts. These are called discrete packets of energy and we call them photons. The energy of a photon is determined by simply h, which is Planck's constant, that's just a number to make all the things work, that never changes, and then f being the frequency of the light or the EM wave that the photon is part of. So that's all this equation here is telling us about. This equation you've seen before in the version V equals F lambda. It's the wave equation. For photons it's always C, because when photons are travelling we talk about them travelling in a vacuum, and when light is transmitted through a material the photons actually are absorbed by one atom and then re-emitted again, and the photons are always travelling at the speed of light in between the space between the atoms and also within the atoms. So even when the speed of light appears to change as light goes through a material, the photons themselves actually stay at the speed of light. It's just that they're being absorbed and re-emitted, and that's how light is actually transmitted through a material. So when light comes through a glass window, the light you're getting out the other side isn't the same light pretended. In effect, the light is being absorbed by each atom of glass and then being re-emitted by each atom of glass, and that process is repeating, and that's why the light slows down as it in effect travels through the glass. So let's look at the first worked example. So we have here energy of a photon of red light with a frequency 4.3 by 10 to the power of 14 hertz. Hertz, remember, is just the unit, it just means per second. So what this means is 4.3 by 10 to the power of 14 full oscillations, full waves happening every second. So using the equation, E equals hf, 6.63 by 10 to the minus 34 joule seconds, multiplied by 4.3 by 10 to the 14 per second, or hertz. That leaves you 2.9 by 10 to the minus 19 joules. The energy of a photon of violet light with a wavelength of 350 nanometers. Remember, nano is by 10 to the minus 9. So using this as the second equation, so you've got the hc over lambda, the Planck's constant, times the speed of light in a vacuum divided by the wavelength, because that bit there is what gives us the frequency. 6.63 10 to the minus 34, 3 by 10 to the 8 speed of light in a vacuum, and divide that by the wavelength of 350 nanometers. The whole nanometer thing is, the reason we have these is so you can just put in the by 10 to the minus 9. You don't have to bother trying to change or convert that number. There's a button on your calculator that does this, definitely worth practicing using that. That gives us 5.7 by 10 to the minus 19 joules. So it says here, this is such a small number of joules that the electron volt is often used as a unit of energy. This is the energy transferred when an electron, so a single electron, moves through a potential difference, something about a power supply, of 1 volt. There's an equation which you've seen a similar version of before, W equals QV. W is the work done to move that electron. So Q is the charge and V is the potential difference. So what that gives you is 1 electron volt is actually a very, very small amount of joules. It's that charge, 1.6 by 10 to the minus 19, times by the 1 volt, which is also 1 joule per coulomb. So 1 electron volt is the equivalent of 1.6 by 10 to the minus 19 joules. So in other words, move that decimal point 19 places to the left. So 0 point, lots of noughts, 16. There are lots of examples in the real world where we use different units to make things easier. So for example, if you were measuring the growth or height of a plant, you might use centimetres, but if you're measuring the distance between worlds, you might use light years or kilometres or something like that. So this is just another example of where we have a more useful unit, the electron volt, to help us make sense of the numbers we're dealing with. So the energy of the photon of red light is 2.9 by 10 to the minus 19 joules, but if we divide that by how many joules there are in an electron volt, that can convert to 1.8 electron volts. So this is just a conversion from one set of units to another. Okay, let's look at the practice questions. If you haven't already tried the practice question yet, then obviously pause this, have a go at it first, and then come back and we'll do the talk through there. Okay, so it's asking about the energy of the violet light photons from the above example, and it wants it in electron volts. So if we look at the previous example, here is the violet light that it's talking about. And we've already calculated in the example the energy in joules, 5.7 by 10 to the minus 19 joules. So we just need to do a conversion. So the energy is 5.7 multiplied by 10 to the minus 19, that's in joules. And if we divide that by how many joules there are in each electron volt, so 1.6 by 10 to the minus 19 joules per electron volt. Put those numbers into our calculator, that gives us 57/16, but because it's physics we're not allowed to leave it as a fraction, so to three significant figures that gives us 3.56 electron volts. So looking at the next question. What is the energy? So working at energy again of a photon, yellow light, but this one has a wavelength of 590 nanometers, and it wants it first in joules and then in electron volts. So we go straight in. E equals HF, which equals HC over lambda. We've got the wavelength here, so we can use that, and we know the speed of light, and we know Planck's constant, so we can put the numbers straight in. So Planck's constant, 6.63 by 10 to the minus 34. Multiply that by the speed of light in a vacuum, 3 by 10 to the 8. Divide the whole thing by the wavelength, so it's 590, but it's nano. Nano means by 10 to the minus 9, so it's 590 by 10 to the minus 9. Strictly speaking, you don't have to put the brackets in, but if you do, your calculator is less likely to do something odd with this. Again, in your calculator, use the fraction button instead of the divide button. It's much more user-friendly and will lay it out as it is in the equation you're using. And also use the by 10 to the power button. Don't actually multiply by 10 and then use the power button. There's a button that has by 10 to the power of x. On some calculators it's shown as a double E, on some it's shown as an EXP. That button is there to help make these work. If you multiply by 10 to the, and then if you multiply by the number 10 to the power of something, mathematically it should work, but depending what else you're putting into your calculation, that's very easy for it to go wrong, and it sometimes attaches the next function to the power, and you end up multiplying by 10 to the power of minus 34 that's been then multiplied or divided by something else. So it's all about using your calculator carefully and sensibly. So if I put those numbers into the calculator, we end up with 3.37 by 10 to the minus 19, and that's joules. So that's the first section done. If we then want to get that into electron volts, we know that, of course, each electron volt has 1.6 by 10 to the minus 19 joules. So we just divide this by 1.6 by 10 to the minus 19, and that's joules per electron volt. Shortcut here, if you are multiplying or dividing two numbers, especially if you're dividing two numbers by the same power, by 10 to the minus 19 here, we could actually just shortcut and ignore that, because that section, the minus 10 by 10 to the minus 19 above and below, that's just going to cancel itself out. So we're actually left with just this number here. But again, if you're less confident, then it's absolutely fine to use the full value and put that in. So again, bunging that into the calculator, not forgetting the minus in the minus 19, not forgetting my brackets. I make that to be an answer of 2.11 electron volts to three significant figures. So let's just look at this section on the photoelectric effect. So some materials, when electromagnetic radiation falls on them, and it was first observed with light, but it can happen with other things as well, some of those materials emitted, gave out, lost some of their electrons. We call those photoelectrons. They're ordinary electrons, but they've been caused to emit by EM radiation, such as light falling on them. That's why the name photoelectron is there. However, what was interesting in the Einstein discovery was, when you've got a particular material, if the light is of a frequency that's too low, nothing happens, no matter how bright or powerful the light was. But once the light is changed to a certain frequency, suddenly you start to get electrons emitted every second. So those electrons, what's happening is they are absorbing energy from the photons that are coming in. If you imagine a different model of an electron, or the atom, sorry, and instead of having your electron shells around the atom, have instead a series of kind of lines or layers that are further apart. I'll have them closer together at the top, and at the top here we're going to call that 0. So that's this top line here. If the electrons have actually escaped away from their atom, they reach 0 energy. All these are minus values. So these are, if you like, binding energies. It's a bit like climbing up a strange ladder. You start off at the bottom, that's when you're mostly held and attracted to the ground, and you have to try and reach up and climb onto the next rung of the ladder to get to a higher energy level. So you're higher up, you've got more potential energy. So this is a higher energy level, but you haven't escaped the Earth yet. You go up another level, you're at an even higher energy level, but you're still not escaped. Eventually, if you have enough energy to get from the bottom right up to the top, you reach this level here, then you've reached 0, because it's like you've escaped the Earth's pull. You've managed to reach space. So the electrons are kind of held in their atoms in a similar way. They have negative amounts of energy that are in effect holding them there, call it a binding energy, and they need to gain energy to reach 0 or more in order to escape. So if they just get enough energy, then the electron might be able to just jump up to 0 and it escapes, but then it doesn't go anywhere, so it's got no energy left over. However, if it's given more energy than it needs to escape, that electron has some spare energy, so it has left over that becomes its kinetic energy, that becomes its movement, and so it can fly off. And that's what this equation here is all about. So what we've got then is the photons coming in are what's giving the electrons the energy. So we've got the photons coming in their wave anyway in the first place, and that's the energy E equals hf, so that's the energy they're giving to the electrons. But then the electrons have to have a minimum amount in order to escape, and this is called the work function. It has this symbol here. Now the work function is the one that any electrons at this layer here, so that's the work function level, they're the ones that are most weakly held to the atom. They're the ones that are most likely to be able to escape. So if you need electrons to be emitted, then you've got to give them at least the amount of energy needed to jump from this level to this level. So it's the energy needed to cross this gap here. And one of the rules about photoelectric effect and quantum physics is one photon coming in can only give all of its energy to one electron. The electrons can't get energy from several photons in one go. They can't get a bit of energy and hang on to it and then save it and then get a bit more later on. What happens is they either get enough energy and they jump up, or they don't and nothing happens. So it's an all or nothing process. So what happens here then is hf on this side is the energy that the photons have that are coming in, and then that's going to equal the work function plus any extra kinetic energy that the electrons have when they escape. And the reason why it says V max is because these electrons, if they get the energy from the photons, they're going to need the least energy to escape, so then the rest of it's going to be their kinetic energy. Electrons at a lower level, they're going to need more of that energy that's the same coming in. They're going to need more of that in order to escape, so they'll have less left over for their kinetic energy, so they will have a smaller speed. So that's why this equation has the V max in it, because the electrons at the work function level, they have this energy coming in off the photons, take away the work function energy level needed to get them to escape in the first place. The rest is their kinetic energy, and they're the ones most likely to escape, so they're the ones that have the maximum possible energy. Sometimes that equation is written in the form kinetic energy max. So, in other words, that section there equals the work function, the energy of the photons, the hf, the energy of the photons coming in, minus the work function needed for the electrons to escape in the first place. So that's the same equation, just in a different layout. So an experiment that can be used to show this is a circuit where you have the radiation with a certain frequency falling on a photocell, and there's a stopping potential, which they've called V subscript S, and that's adjusted to the same PD needed to just reduce the current to zero by stopping all of the electrons that are being emitted. So in other words, what's happening there is light is falling on the material, electrons are being emitted and want to fly off, but that potential difference is being applied back to them to hold them just in place. So this shows that the potential that's pushing back against it, multiplied by the charge on the electrons that it's pushing back, that is equal to the kinetic energy that those electrons have, because that's just cancelling out the kinetic energy. The electrons are trying to move, but that is pushing them back with exactly the same amount of energy, so they end up sitting still. And the reason, again, it's V max is because it's talking about the ones that are most easily able to escape, so they're the ones that have the most kinetic energy. So you can again combine those. So HF is the energy of the photons coming in. Work function there is the minimum energy needed that's going to be used up out of that HF first before they escape. And then, of course, this is the stopping potential. Combine those, and then you get this equation here. So what this has shown us is that you've got the energy of the photons coming in on a single charge, plus the energy of the photons at the minimum frequency per unit charge, and it's the difference between the two that gives us that stopping potential. As always, what we're looking for in physics is something that will hopefully give us a straight line, because then we can use that to work out what's going on. So in this graph here, we have Vs, the stopping potential at the side, and we have the frequency of the light coming in at on the bottom. So this, if you change the frequency and get a whole range of results, this shows what the threshold frequency is of that material, because those are the ones where the electrons are just gaining enough energy to escape, but there's the smallest amount of potential difference needed to stop them, i.e. 0. So at this point, the electrons are gaining energy just escaping, but have got no kinetic energy left over. Any higher frequencies of the radiation coming in, those electrons have spare energy, so they would move with that kinetic energy, which is why you then need to apply voltage in order to stop them and cancel out that kinetic energy that they gain. Let's look at the worked example. So the experiment they're describing here, you have the setup we described before, and you alter the frequency of the incoming radiation and see what stopping potential you need in order to cancel out the movements of the electrons that are being emitted. So the higher the frequency, the more energy the photons have coming in, so the higher the stopping potential you need to work against the electrons that are being emitted because they absorb that incoming energy from the photons. So gradients is something that sometimes can be a bit of fun for people. Remember, a gradient is how much up has the thing gone for every one across. So that's why it's the delta y, the change in the y-axis values, divided by the delta x, the change in the x-axis values. You can pick anywhere along a straight line to take your gradient from. Generally, the larger the gradient, the better. So in here, they've gone 3 volts is at 12, and they've gone down to 0, which is at 4.4. So 3 minus 0 is obviously 3, and the 12 down to 4.4 is 7.6, but not forgetting the scale on the axes just there, 10 to the 14. There's the gradient, and then the units are just y-axis units divided by x-axis units, hence volt seconds over here. So it gives you the gradient, and from the previous thing we know gradient is h over e, and we know h, so therefore we can work out the value, and there it is. So this gives a Planck constant in the graph of 6.3 by 10 to the minus 34, and we actually know it's 6.63, so that's pretty close. Percentage error is something that you'll do at A-level in a lot more detail, so don't worry too much about this, but the crux of it is we've got the difference between the accepted result, the result we've got, So the difference between them, out of, or as a share of the actual result we should get, times that by 100 to make it a percentage, and that gives you what's called the percentage error. Often referred to as something called the percentage uncertainty. This is something that we do in lots of detail in the A-level. So with that in mind, let's have a look at the practice questions just here. So again, if you've not done the questions yet, pause it now and then have a go, and then I'll go through the explanation in just a moment. Okay, so first one, we're looking here, work function for sodium is 2.46 electron volts, and it's calculate. We like calculate questions because they mean you're going to use some equations and put some numbers in. Lowest frequency that will cause emission of photoelectrons from the surface of sodium. So, thinking about what happens, we've got the energy of the photons coming in will equal the work function plus the maximum kinetic energy of any emitted electrons. So the lowest frequency that causes emission is the electrons that just escape, or the photoelectrons that just escape when they have zero kinetic energy. In other words, they only just gain enough energy from the incoming photons to escape their atom, but they don't have any energy left over in order to move off. So actually, the equation just becomes HF equals the work function. So the work function is 2.46 electron volts, but we need to convert that into joules in order to be able to work out the frequency. So remember, if 1 electron volt is 1.6 by 10 to the minus 19 joules, then obviously 2.46 electron volts, multiply that by 2.46 to get how many electron volts we've got, how many joules we've got, sorry, and that gives us 3.936 by 10 to the minus 19 joules. HF equals that number now, 3.936 by 10 to the minus 19. So the frequency is just going to be your 3.936 by 10 to the minus 19 divided by the Planck constant, which is 6.63 by 10 to the minus 34. Put those into a calculator and we get 5.94 by 10 to the 14 hertz to our three significant figures. At A level, you get a sheet with things like the Planck constant and some of the equations on it anyway. In fact, I think you get all the equations you need at A level, or you get the equations you need to build them together. So in some aspects, slightly nicer than the GCSE with that. So you don't have to memorize the values of these constants. They are on the data sheet that you get. So if we have light with a different wavelength, then we can work out what the maximum kinetic energy is going to be. So, same equation. So the HF is the energy of the photons coming in, so that equals the work function plus the Ke max, so rearrange that. So the energy of the photons coming in minus the work function, i.e. the minimum energy electrons need to escape, that will give us the Ke max. So then we just have to put our numbers in. We have the wavelength, of course, so we perhaps need to turn that into a frequency, or we can just use the fact that HF is also Hc over lambda, so let's put it straight in there, minus the work function equals the Ke max. Let's move that up a bit and stick some numbers in. So we've got 6.63 by 10 to the minus 34. That's the Planck's constant. Multiplied by 3 by 10 to the power of 8. That's the speed of light in a vacuum. Divide that by the wavelength, which is 450. Again, it's nanometers, so by 10 to the minus 9, that's the nano. Minus the work function that we just had as 2.46 electron volts. But now we've got mixed units, so we need to convert the 2.46 electron volts into joules. So remember, each electron volt is 1.6 by 10 to the minus 19 joules, so it's joules per electron volt. So we need to do that conversion, so 2.46 multiplied by 1.6 by 10 to the minus 19. So this section here, the energy 2.46 electron volts in joules is actually 3.936 by 10 to the minus 19 joules. If we also work out the first section, the HC over lambda, put those into our calculator again, fraction button, brackets, power to the 10 button, then that gives us 4.42 by 10 to the minus 19 joules here. So 4.42 by 10 to the minus 19 joules minus the 3.96 by 10 to the minus 19 joules, 936, sorry, by 10 to the minus 19. That gives us an answer of 4.9 by 10 to the minus 20 joules, or for sake of convenience, that's going to give us 0.49 by 10 to the minus 19 joules to make it an easier comparison. Again, shortcut here, if we're subtracting two numbers with the same by 10 to the power, we can actually just ignore the powers and just do for 4.42 minus the 3.936. And that would leave us with the 0.49, having to remember to put the power then back on, otherwise we end up with a very different number to the one we want. Okay, I'll clear that and then we'll have a look at question 4. So we have light wavelength of 290 nanometers, and it tells us this time the maximum kinetic energy. So we're starting in the same place. HF, the energy of the photons coming in, is going to go into the work function to cause them to escape, and plus any left over is going to become the kinetic energy of the electrons that do escape, and therefore it's the maximum kinetic energy possible for the electrons that are most easily able to escape. So we're trying to calculate the work function, so rearrange that. HF minus the kinetic energy max will equal the work function. We don't know F, but we do know the wavelength lambda, so that becomes HC over lambda minus the kinetic energy max equals the work function. And then it's just a case of putting our numbers in. The 2.19 electron volts. 2.19 electron volts, remember each electron volt is worth 1.6 by 10 to the minus 19 joules. So there's that many joules per electron volt, so we can convert that first of all. So 2.19 by 1.9 by 10 to the minus 19. Again, not forgetting the power button and the brackets. That becomes 3.504 by 10 to the minus 19 joules. So that's what we need to use here. If we're going to subtract this value, kinetic energy max, from this HC lambda, the energy of the photons coming in. Let's put in the numbers we've got for over here. So Planck's constant, 6.63 by 10 to the minus 34, multiplied by the speed of light, 3 by 10 to the 8. Divide the whole thing by the wavelength, that's 290 nano, so by 10 to the minus 9 meters. And if we put all that together, we can do it in sections. We get, we've got here 6.86 by 10 to the minus 19 joules, minus the 3.504 by 10 to the minus 19 joules, which leaves us with 3.35 by 10 to the minus 19 joules, which we could convert to electron volts, which will be, that gives us, so divide that by the 1.6 by 10 to the minus 19 joules per electron volt to convert it, that gives us 2.1 electron volts. We could have, if we wanted to, when we worked out the HC over lambda in joules here, we could have converted that into electron volts there, left the Ke max as electron volts, and done electron volts minus electron volts, and it would have got us to the same answer. So it doesn't actually matter. The key thing is when you're dealing with the HC over lambda or the HF section and the work function or kinetic energy max function section, you've got to make sure you're dealing with the same units on both sides. So you can't have joules one side and electron volts the other. So you can either convert one set into it to make them all electron volts or make them all joules. Doesn't matter which way you do it, but you've got to make sure you're consistent on both sides of the equation and within each variable that you're using. Now, bear in mind, of course, when you actually study this topic, you've had a 30-minute video clip and a couple of shorter clips going through it. It's actually a good sort of 2-week, maybe even 3-week topic to go through it in any detail, but hopefully that's giving you a flavour of the sort of thing you can expect. And remember, at all times, physics is common sense wrapped up in silly words and equations. So once you get past that, actually a lot of this is quite nice. Okay, hope that all makes sense. Enjoy.